For some reason wants to like not do real analysis on the nights. It'd be great, but I'm gonna go talk to him about it.
Good luck. All right, so. Wait.
Modern's gone. No, but it's all at 300, kids in 300 right now. You know what? They haven't taken Cal 3.
In modern?
No, not modern. In 300. None of those kids have taken Cal 3, except one of them. No. Yeah, they all took Cal 1. They're in differential equations in Cal 2 right now.
What?
Yeah.
That's no bueno.
Yeah, it's not. Yeah. Actually, I think it might just be one of them. But I know Will's probably going to have to take that course. I thought he was transferring, but then he told me he wasn't transferring. Yeah, that's what I thought too. Yeah. Yeah, he's math ed. Yeah, I thought he was in the engineering, yeah.
All right, so basically here's a summary of how to get components of a vector field, a one-form field if you like, and a two-form. So in every case, we can think about the components in terms of the frame or the coframe. So for the vector field, of course, this is most familiar, even from Calculus 3. We want to calculate components. We take dot products with respect to the given orthonormal basis, right? For a one-form, you can pick off components by evaluating the form on the adapted frame, and then that gives you the component corresponding to that coframe. And same here. And then for a two-form, well, there's just one component, and you can get it from evaluating on the pair of the adapted tangent fields, E1 and E2. All right, so lemma. Well, I guess rather than state the lemma, I'm just going to sort of work it out. All right, so the let's see here. I guess I should just remind you what was the formula for, I'll put it up high. You guys remember Gaussian curvature, determinant of the shape operator, right? Mean curvature, 1/2 the trace of the shape operator, right? And so we can calculate determinant and trace using the matrix of the shape operator with respect to any choice of basis that you like. So of course the choice of basis we're going to use here is the adapted frame, right? Because we already got the formula right here sitting in front of us. Here's the formula for the shape operator in the adapted frame. So if you look at that, S of E1 is what? Omega 1, 3 of E1 plus omega 2, 3 of E1, E2. I'm going to omit the P if you guys don't mind. All right. I hope that doesn't make this argument pointless. Sorry. I blame the cutie. Let's see here. E2, omega 1, 3, E2, E1, plus omega 2, 3, E2, E2. All right. So if we let basis beta be E1, E2, right? And so I really do have a specific point in mind. All right, I'm fixing a point, I'm just not writing it. Okay? Then what's the coordinate vector of S of E1 with respect to the beta basis? Well, it's the coefficients which I need to write S of E1 is a linear combination of the basis, right? So this is my first component, and that's my second component. So I've got omega 1, 3, E1, omega 2, 3, E1, all right? And likewise, the coordinate vector of E2 with respect to the beta basis is this end of that, because those are the coefficients needed to expand, the weights needed to build S of E2 as a linear combination of the basis E1, E2. So that's omega 1, 3, E2, omega 2, 3, E2. And so you guys remember how it goes. The matrix of S with respect to the beta basis in my notation is this and that next to each other, right? So this implies then that the basis matrix for the S shape operator with respect to the beta basis is omega 1, 3, E1, omega 2, 3, E1, and then next column, omega 1, 3, E2, omega 2, 3, E2. So, okay, what's the determinant? What's the trace? So the determinant of S is omega 1, 3, E1, omega 2, 3, E2, minus omega 1, 3, E2, omega 2, 3, E1. All right, so we have that. And what's the trace? It's omega 1, 3, E1 plus omega 2, 3 of E2. Okay, so now we got these. We're going to save these for our future reference, okay? Those are formulas. I mean, that matters because,
Wouldn't it be 1/2 the trace then?
well, that is the trace. But you're right that this first one is the Gaussian curvature, right? And this one would be twice the mean curvature, right? Very good. Okay. Now I will state lemma 2.2. Which says that number 1, omega 1, 3, wedge omega 2, 3 is the Gaussian curvature times theta 1 wedge theta 2. And 2, it says that omega 1, 3 wedge theta 2 plus theta 1 wedge omega 2, 3 is equal to 2 times h times theta 1 wedge theta 2. All right. That's lemma 2.2. Now, the proof is very simple because all we have to do is just take that wedge product, all right, So like omega 1, 3, wedge omega 2, 3 is omega 1, 3, E1 theta 1 plus omega 1, 3, E2 theta 2 wedged with omega 2, 3, E1 theta 1 plus omega 2, 3, E2 theta 2. So I'm expanding the connection form 1, 3 and the connection form 2, 3 using the coframe basis as I started. Oh, did I start the camera?
Yeah.
Oh, phew. I had this moment of like, I don't remember doing it.
That sucks when like you leave your house and you're like 20 minutes away.
Oh, I know.
You're just like, well, we're wrong.
So the thing is, theta 1, wedge theta 1, 0. Theta 2, wedge theta 2, 0. So all you got to think about here is you got omega 1, 3, E1, omega 2, 3, E2, minus omega 1, 3, E2, omega 2, 3, E1, theta 1, wedge theta 2. Where'd the minus come from? It came from the fact that I had to, these two guys here, when I wedged those, I had to do the opposite order to put this minus here on these two terms. Yeah. And what is that? That is this.
The determinant.
That is the determinant of the shape operator. That's the Gaussian curvature. So there you go. That is K, theta 1, wedge theta 2. And notice that you see why this is called Gauss's equation. Maybe you start to appreciate it more. See, that's omega what? Omega 1, 3, wedge omega 3, 2. So you can change that to a 2, 3 if you also change this to a 2, 1, right? So this is equal to d omega 2, 1 by Gauss's equation.
Oh, this guy was dead like before any of these things happened.
Yeah. What's that?
I didn't know he died so like he lived his time period. He was in the 1700s to 1800s.
Yeah, I mean he was your age, around like 1800. And he wrote his disquisitions arithmetic when he was, like about college age. And it took number theorists the better part of 50 to 70 years to unpack it for people so that they could understand it. Research people could understand it. Essentially what he did was to work out relations in modular arithmetic that were very technical and difficult, things that had been before tried with other methods. And basically he gave up on those other methods because they were slightly heuristic, and just through a technical tour de force just plowed through all this, modular arithmetic.
Why are a lot of things in physics named after him then?
Because he also did work in, flux integrals and differential geometry. I mean, he did everything. Yeah. Let's see here. So you're fine. And so where was I? And then, okay, the other one. And the proof of 2 is very similar. Like you can almost see it already. What happens, what is omega 1, 3? Omega 1, 3, wedge theta 2, plus theta 1 wedge omega 2, 3. Well, think about that. The 1 component is the only one that matters. The 2 component vanishes there, right? Because theta 2 wedge theta 2 is 0. So I can just simplify that to omega 1, 3 E1. And then this theta 1 wedge theta 2. And then this one, theta 1 wedge, well, the only thing that matters here is the 2 component. So omega 2, 3. And why is that? Because the other one, I mean, I could write it down, but it's just going to wedge to 0. So why bother? And so you put that together, you got omega 1, 3 E1 plus omega 2, 3 E2 times theta 1 wedge theta 2. And I'm sorry, I do try to write the indices up on the thetas, but I don't think O'Neill does, and so I'm sometimes forgetting to put my indices up on my thetas. I'm not going to take off points if you put them up where they should be down, or vice versa. I'm not that careful, so I can't really assume that you're that careful either. Certainly have bigger fish to fry, if you believe in that sort of saying. And what is that? Well, that's the trace. So that's 2h. There you go. Now, of course, you could also write this minus d omega 1, 2, right? That's another choice you have. You can either see the 2, 1 versus the 1, 2. So there's a minus, and so like one of the equations I just noticed in the notes I have is like d omega 1, 2 is minus k theta 1 wedge theta 2. You just got to beware that the order of the form components matters. All right. So with all of this, let's calculate, now that we can, the Gaussian curvature of a sphere. All right, let's do it. Now, to do that, I should have been working with 2 boards, and I should have been saving our coframe calculation with the spherical coordinates that we did earlier, right? But sadly, hey, you guys have been around here a little longer than I have. Does there exist a room with like 2 boards like this somewhere?
This is the only classroom I've ever been in with a blackboard.
Maybe I should just like donate 2 like choice blackboards to the school, and like.
I'm just gonna buy one myself too. I just gotta ask Dr. Reckler.
And then, but then what would happen would be like, that room would then become a chemistry room or something. Like, no, I will take my boards back.
Not if you put them in bib grades, because they don't have chemistry classes anymore.
Well, there is no bib graves.
Oh yeah.
Math and science, whatever. What is it called now?
The math and that.
At least math is first.
That was exactly what I said. I said at least math is first.
Yeah.
I'm gonna call it bib
No,
grades
wait,
so
it's
they add up.
alphabetical. That's why.
Oh, it is.
I think
It will always be bib graves in our hearts.
I said it to someone this
Wasn't he
morning.
racist or something? She racist. You racist.
Yeah, that's why.
Yeah, that's why they changed it.
I'm just so used to calling it bib grade.
Yeah.
And I mean, I'm not mad. I'm excited to change the name, but it's just like, I'm going to remember it.
Well, anyway, before we graduate.
My coach was like, everybody's gonna refer to it as fifth grade until the next class comes in.
So we have rho equal to r. I'm trying to remember. So you guys have to remind me. Theta 1 was what? And what was theta 2?
For which one?
I'll just write it down. R d phi. And this one was r. I got r sine theta.
No, r sine phi d
So,
theta.
yeah, sine phi d theta. What? Oh yeah, d theta.
Yeah, that's it.
All right, and we worked out that omega 1, 2 is in fact cosine phi d theta. All right. So what does that make omega 1, 2? Omega 1 wedge omega 2 is r squared sine phi, right? D phi wedge d theta, right? Okay. And what's d omega 1, 2? So we have to do the exterior derivative of cosine phi wedged with d theta. That's the definition of exterior derivative. What's the total differential of cosine phi? It's minus sine phi d phi, right? Right. So what's going on here? This we've got right here, right? So if you tilt your head and squint, you can see what we have is minus 1 over r squared theta 1 wedge theta 2, right? Because if you like, you could solve this for theta 1 theta 2 over r squared is equal to sine phi d phi wedge d theta, right? But what else do we know? We know that d omega 1, 2 is minus k theta 1 wedge theta 2, right? So you look at this, and you look at that. And the coefficients have to match. So this shows you that the Gaussian curvature of a sphere is 1 over r squared. Trust me when I tell you that this is considerably easier than going through the EFG LMN business for the standard like spherical parameterization of a sphere. I mean, it took us a while to get here, but once you're here, this is like a pretty nice calculation. And let's see here. What about the cylinder while we're here? Oh, what would the can we? I'm trying to think. Can we get the mean curvature? What we need to do to get the mean curvature here? What do I need to do? I don't know if I can do that without. I need omega 1, 3. Oh, I guess I don't know omega 1, 3, do I?
Yeah, omega 1, 3 wedge r sine phi theta.
Right, but the trouble is I don't know what omega 1, 3 and omega 2, 3 is for the adapted spherical frame. I haven't calculated those. You know? And there's a suspicious absence of that calculation from chapter 6. Okay, so.
No, there's a structure equation that popped out.
Yeah. Now, for the cylinder, well, the cylinder is kind of boring. For the cylinder, I won't even write it down, but what we found for the cylinder was that omega 1, 2 was what? We found omega 1, 2 was 0 for the cylinder. So that tells you that the Gaussian curvature of the cylinder is 0, because d omega 1, 2 is Gaussian curvature times theta 1 wedge theta 2.
Also, we found too with the GLN.
Right. But in this world, the proof that the Gaussian curvature of the cylinder is 0 just comes from omega 1, 2 being 0. All right. So next up, we start talking about some special kinds of frame fields. There's also something called a principal frame field. What do you think a principal frame field is going to be? I I think I can erase everything now. I think I can. Famous last words. Yeah. All right, so definition, principal frame field is an adapted frame field on M such that E1 and E2 are principal vectors, principal vector fields. I'll just say principal on M. I'm tired of writing. What's that mean? What does it mean to be a principal vector field? That means that S, the shape operator, right, on E1 is just equal to what? It's equal to K1E1. And the shape operator acting on E2 is K2E2. In other words, at each point in the surface, the E1 and E2 point in eigenvector directions for the shape operator. They point in the directions in which the shape operator just acts by multiplication by a scalar. And the K1 and K2 are the principal curvature functions. All right? Lemma 2.5. If P is a non-umbilic point, what's that mean? What's an umbilic point? Non-umbilic point of M. Then there exists a principal frame field on some neighborhood of P. So I'll remind you, umbilic point is one in which the principal curvature function is constant in all directions, like K of U is constant in all directions. All right, so the proof is this. If P is non-umbilic, neighborhood, so close to P, close enough to P, that implies that K of U is non-constant at P, all right? Which means that K1 of P is not equal to K2 of P. Right. Which also means that K1 minus K2 of P is not equal to 0. I guess I'll write the P there. Right, or So what does that mean? So I say is, okay, well, we've also have arguments that say that the principal curvature functions are continuous. All right? As he mentions, they're continuous. They're not necessarily differentiable, but they are continuous. Well, there's many points where they're differentiable. He explains earlier in chapter 5, I think. But anyway, the point is that what you have is that k1 minus k2, this function, and that's the difference of continuous functions, which is, again, continuous. It's not equal to 0, right? So one of the things we learn in analysis is if you have a continuous function which is non-zero at a point, it can't just all of a sudden jump to 0 infinitely close to the point, right? Like there has to be some epsilon neighborhood, if you will, of p on which it continues to be non-zero. This is something we know from analysis. So the fact that k1 and k2 are both continuous, the difference is a continuous function, non-zero at a point implies non-zero in a neighborhood of a point. So, and then what? I'll call that neighborhood of P. Well, and then he argues that, okay, so what you can do is you can string together the principal vectors for k1 and the principal vectors for k2 and put them together into a vector field for all such q. And those vector fields, E1 and E2, constructed in that way, will form a principal frame field. So, as I say in my note here, there's more detail in the book, but that's essentially it. So, moving along. So what can we say in this very special context? What do we get to say about the connection coefficients? I'm going to erase this here because I think we're done with this. So okay, so S of E1 is also equal to what? S of E1, remember we had 1, 3. See, I told you I shouldn't have erased it. E1, I can't win. Omega 2, 3, E1, E2. All right, so because these are, because we're looking at the moment, we're considering a principal frame field. We know that the top one is equal to K1 E1, and we know that the bottom one's equal to K2 E2. What does that say? Well, for one thing, it says that the E1 coefficient must be 0 in this one. And it says that the E2 coefficient must be 0 in that one, right? And then, because we can equate coefficients for a basis, it must be that omega 1, 3 E1 is equal to K1, and it must be that omega 2, 3 E2 is equal to K2. And indeed, that is what we have. So thus, omega 1, 3 E1 is equal to K1, and omega 2, 3 E2 is equal to K2. But we also, these things I've arrowed to 0 are important as well, because that means that there's no like theta 2 piece of the 1, 3 form. Right, so this piece, the omega 1, 3 E2 is 0. Omega 2, 3 of E1 is equal to 0. So by the comment I had up in the corner of the board, building the forms from their component there up there, this tells us that omega 1, 3 is in fact K1 theta 1. And this tells us that omega 2, 3 is K2 theta 2, which is what I have written here. Yeah. Now, let's just take a second here to smell the roses, so to speak. What was our formula for, what was Gauss's equation? Do you remember? What was it? It was d omega 2, 1 is omega 2, 3 wedge omega 3, 1. Is that right? Did I get it? You guys gonna make me look at my notes? How dare you? How dare you?
I think it's wedge, omega 1, 3 wedge, omega 2, 3,
Omega 1,
3 wedge, omega 2,
1, 3, 2, 3. Well, this would also be equal.
Oh, yeah,
This would also be equal to omega 3, 1 minus omega this, right? Which would be equal to omega 1, 3. There are indeed many flavor options here in terms of like reordering stuff. Yeah. Okay, so, but here's what I'm trying to get at for the moment. But we know that this is equal to what? K, theta 1 wedge theta 2, right? And what is omega 1, 3 wedge omega 2, 3 equal to? For a principal frame, it's K1 theta 1 wedge K2 theta 2. Also known as K1, K2, theta 1 wedge theta 2. What does this tell us about the relation between the product of the principal curvatures and the Gaussian curvature? It tells us that the Gaussian curvature is the product of the principal curvatures, which of course we knew already, but it's kind of cool to see it again here derived from the algebra, wedge products and such. Now, this theorem that I'm about to write down has some really, really neat consequences. So, so E1, E2, E3, principal frame on M, then E1 acting on the second principal curvature function is equal to the difference of the principal curvature functions, K1 minus K2, times omega 1, 2 acting on E2. And E2 acting on the first principal function, curvature function is K1 minus K2 acting on omega 1, 2 of E1. All right. Let's see here. I think I start with, let's see, which one is that? Is that one of the Cauchy equations? D omega 1, 3 is omega 1, 2 wedge omega 2, 3. I think that's one of the Cauchy equations. So recall d omega 1, 3 is equal to omega 1, 2 wedge omega 2, 3. All right. But what else? We're working with a what? With a principal frame field, right? So we still have the previous formulas we just got. So omega 1, 3 is K1 theta 1, right? And what else? And we also know that omega 2, 3 is K2 theta 2. So what we're looking at is omega 1, 2 wedge omega 2, 3, which was K2 theta 2. All right. Then, so this is a product, so I can do the Leibniz rule. Okay, and this is dk1 wedge theta 1 plus k1 d theta 1. All right. And that's, of course, still equal to, I can pull the k2 out if I want, k2 omega 1, 2 wedge theta 2. All right. Then what do we do? I group stuff. I put all the omega 1, 2. Well, d theta 1 is what? That's what I got to do. D theta 1 was, what was d theta 1? We had a form. That was, what was that? That was. Oh no, for an arbitrary. What's the structure equation? It's like the no, the abstract structure equation, not specific to one of those examples, but
d theta 1 equals omega 1, 2 wedge theta 2.
Yeah, that one. So see that this is omega 1, 2 wedge theta 2 again. In other words, this d theta 1 is the same as that. So I can rewrite this as dk1 wedge theta 1 is equal to k2 minus k1 times omega 1, 2 wedge theta 2. All right. And then it looks like I do something sneaky. Yes. So I apply again. So this is got to be on our game here. This is a one form, right? So we can expand that in the theta 1, theta 2 basis. So this is dk1 E1 theta 1 plus dk1 acting on E2 theta 2. All of that wedge theta 1. I mean, that's what this is. So, of course, this piece is not there, right? Because, that one piece goes away because theta 1 wedge theta 1 is 0. And what we get is, dk1 on E2 theta 2 wedge theta 1 is equal to, well, k2 minus k1 omega 1, 2 wedge theta 2. Now, do you remember the relation we had? So now I'm going to have to go back a bit here. Remember we had this df acting on v is v of f?
Yeah.
Okay, so think about that here. The function in question is k1.
Wait, but V is just like the differential.
Vector field. So
Yeah.
this is E2.
Yeah.
So this, yeah,
Yeah, E2 of K1 or DK1?
yeah, E2 of K1, right. But, and I think there's a typo actually, because, well, okay, fine. Well, this here, right, also, we can do the same trick over there too, right? This is omega K2 minus K1, omega 1, 2 of E1, theta 1 wedge theta 2, right? No loss of generality there, because the E2 component would give you theta 2 wedge theta 2, which would not be present, right? So I can do that there. So it looks to me, unless I've made a mistake here, like there's a minus sign missing in the statement of the theorem, right? It should have been E2 on K1. See, because I got theta 2 wedge theta 1 here, and I got theta 1 wedge theta 2 here. So this implies to me that E2 K1 is equal to, you could write it this way, K1 minus K2, omega 1, 2 of E1 theta, there's no theta, I'm reading off the coefficient of theta 1 wedge theta 2, so that's the relation. So to fix what's up there on the top, I could put a minus right here if I wanted. And I'd feel better about that because there was a break. When I wrote that theorem, it bothered me because it wasn't symmetric with respect to 1 and 2. And there's a symmetry here abstractly with respect to 1 and 2. What's the difference between 1 and 2? Formulas we write for an adapted principal frame field should be symmetrical between 1 and 2 unless there's some other reason for there not to be the symmetry, right? Because 1 and 2 are just principal directions. There's no preference of one to the other. The equations that appear ought to be symmetric in 1 and 2. And they weren't before I put that minus there. So anyway, that's how you prove this. And the proof of the first one is almost the same. It's just, instead of looking at that Codazzi equation, you look at the other one, like the d omega 1, d omega 2, 3 is equal to the other, and go from there. Now, once you have this, you can do some kind of interesting stuff with it. Where'd it go?
You're on page 12.
Yeah. That's just the other half of the proof, right? I say, remark, this theorem shows that for principal frame, omega 1, 2 controls the principal curvatures K1 and K2 and how they change. Yeah. See, because E1, what this is kind of telling us how K2 changes in the E1 direction. Remember that this vector field acting on a function is a directional derivative, essentially. So this is telling us about the change of K2 in the E1 direction. And this formula says it's controlled in some sense by this 1, 2 coefficient. And of course, it also matters what K1 and K2 were before you think about this. But all right, so I think that brings me to my lecture 19. But what I'd like to do with the remaining time today is to actually skip ahead and talk to you about lecture, excuse me, 20. So basically 19 on surface theorems, it's just applying the formulas we have to say some specific things for like various cases in terms of like, does the surface, does it like, how does it relate to a plane? Is it part of a sphere? And so I'll come back to that. But what I wanted to do was just spend about little bit of time here talking about lecture 20. So I want to explain to you what lecture 20 says without proving everything, okay? So we need a couple definitions here, but that's the main thing. One is, how do we define distance on a surface? Like, what would distance on a surface be? So here's the surface, right? Maybe there's a hole in it, whatever. And you got a point P. You got another point over here, Q, right? What's the distance from P to Q on the surface? And he uses rho, which is annoying to me. But he apparently uses rho from P to Q for the distance. Distance on the surface M. How would you calculate that?
Did you not make a function that lies on the curve or the plane?
Right. Oh, so you say take a curve on the surface like that one. Maybe call that alpha, and say that this is equal to, I don't know, basically like the arc length of alpha, right?
Yeah.
So what would the formula for the arc length of alpha be? Well, we could say, but the thing is, yeah, I mean, there's that curve, right? But what about all the other curves? Like, how do you choose which curve to define the length by? Because there's also one out here, right? And maybe there's one here. And maybe there's the best one that would be like right here, but you can't go there, right? So it can kind of only approach that even. Maybe you can't get to the curve. Like you can, maybe you can kind of approach a family of curves, which makes the distance between P and Q3, but you can't actually make a curve that makes the distance between P and Q be 3.
Well, if we imagine the patch wasn't there, could we not write a straight line or a straight curve?
But yes, but we're
and then draw something off of that.
Yes, but we are staying on the surface in our thinking here. So we have to, or whatever definition we're giving, it has to be just involving the surface. It can't go off surface.
We usually use that.
No off-world trips.
What are they called?
It's forbidden.
TV plus P minus Q. Is that?
Right. Yeah. Right. Yeah. In Euclidean geometry, we just calculate the length between the points. The crow flies, right? I mean, but here, what we want to do is you want to calculate the infimum, the greatest lower bound of the length of alpha, such that alpha is curve on M from P to Q. And the length of alpha, well, that we define like a la calculus 3, right? It's the integral from, say, T1 to T2 of the length of alpha prime of T dt, right? Where alpha of T1 is P and alpha of T2 is Q. So the usual arc length calculation. So that's what's meant by distance between points on a surface. It's, you have to, I'm trying to think of a good example where the inf is needed because the path which achieves the shortest length, it might just be out of reach. And yet that's what you want the distance to be for logical reasons. I'm trying to think of an example of that. But anyway, that's of course, the inf may not be necessary. Like, it might just be attained by a particular curve, right? So like on a sphere, if you want to calculate the distance from this point to this point, you just, the curve that gets you from there to there in the shortest distance is one of those great circles. you know? And like, technically speaking, you don't really need the infimum or the greatest lower bound here. You just look at the great circle, calculate the arc length between there, and that's the distance.
Didn't you do that on here too? Like say there's a circle that connects P and Q that goes around the...
But I get into logical trouble because I want...
Oh yeah, you're assuming that the plane is, or the surface is flat.
Yeah. Okay, so this is the distance between points on a surface, all right? Next definition.
Wait, could you not like, because you know how you can look at a surface 2D?
Mm-hmm.
Could you not make a circle on the 2D and then explode it up into 3D?
Let's see here. How about this? We take the hemisphere, right? And we delete this point.
Okay.
I believe that's still a surface.
But there's a hole.
It's annoying, but it's still a surface. So if you want to find the distance from this point to that point, you know, the great circle which connects them,
Doesn't exist.
it's outside the surface, right? But if you take like all of the curves that get closer and closer to that great circle, they get closer and closer to that distance. And that's what you want the distance to be, even though you can't actually achieve it with a particular curve on the surface.
This is essentially a limit.
It's annoying. Yeah. You guys don't talk about infimum or greatest lower bound in reals?
Didn't take real analysis.
Oh, I'm sorry. What am I? I'm an idiot. Why don't I should remember what you've taken. Okay, so definition. An isometry. Oh, back to isometries again. Here we go. Definition. An isometry of surfaces surfaces in R3 is an injective map for which I'll just say such that the push forward of V dotted with the push forward of W is equal to V dot W for all V and W in the tangent space to P and M. I say thus the differential of an isometry is invertible since this condition, right? This condition implies that F star is invertible and lots of other nice things, actually. It's much stronger than that. That was the condition which gave us that it was an orthogonal transformation, right? Which is in fact linear if it's, it's linear and it satisfies that very nice orthogonal transformation stuff. So let's see here. So in this case, it follows, in fact, then that the inverse of an isometry is also an isometry because